PE4332 pulsed eddy current flaw detector detects metal corrosion under insulation with thickness up to 300 mm. The device does not need any surface preparation including insulation removal. The method of pulse eddy current testing enables assessment of metal volume ratio in a space underneath the sensor. This allows detecting the common area corrosion in pitting located both on the outer and inner metal surfaces. To validate the method, let's measure test steel discs with thicknesses of 10, 5, and 2 mm respectively. The measurements will be carried out through insulation pieces with thickness from 50 mm to 300 mm. We'll check whether the device can see the difference in steel thicknesses of these three discs. After test pieces, we'll proceed with real pipes where casings will be installed in addition to insulation. Before taking measurements, let's talk a little about the method itself. The measurements begin by applying a sufficiently long current pulse to the sensor coil. This current generates a magnetic field that completely magnetizes the test object. When the current is interrupted, eddy currents arise in the test object, preventing demagnetization of the object. The thicker the metal under the sensor, the longer the demagnetization of such object. Thus, the method is based on dependence of the test object demagnetization rate on the object thickness. The device displays a diagram of the test object demagnetization over time and the metal wall thickness calculated according to the demagnetization rate. The sensor has a working aperture comparable to the size of the sensor itself. About 90% of this area provides a response signal to the receiver of the device transducer. Due to this measurement method, we won't be able, on the one hand, to see small cracks and defects that are significantly smaller than the sensor surface. But on the other hand, the device perfectly measures large areas of corrosion through the insulation and casing. Let's skip directly to the measurements, starting with a small sensor and a small insulation thickness of 50 mm. Before taking the measurements, it is important to set the parameters of the test object and to carry out a quick calibration. The calibration must be carried out on each new test object. In addition, we recommend to carry out calibration when there is a clear change in the physical parameters of the test object, for example, a visible change in the thickness of the insulation. Let's carry out a calibration measurement where the metal thickness is known. When changing the sensor, we also recommend to carry out a one-time calibration away from the metal objects, for example, by raising the sensor by at least 50 centimeters above the pipe. The calibration is completed and we move on to measuring the thickness of the discs under the insulation models. As the device doesn't measure directly the wall thickness, the thickness measurement accuracy is 10%. However, in practice, we see good reproducibility of results both for 50 mm and for 100 mm thick insulation and an obvious change of the demagnetization diagram and measured wall thickness in such areas where the pipe thickness actually changes. For insulation thicknesses up to 200 mm, use a middle-size sensor. Don't forget to calibrate. The demagnetization curve depends on the insulation thickness, so it is important to set the correct calibration parameters for correct calculation of the test object wall thickness. For insulation thicknesses up to 300 mm, use a large sensor. During real work, select the sensor based on the insulation thickness of the test object and on the corrosion areas you would like to detect. As we see, the sensor successfully got through the 300 mm insulation. The PE4332 pulse eddy current flaw detector has demonstrated good results on test steel discs, and we can proceed to measurements of a rail pipe with insulation and casing.